Hello, everyone. This is Peng Hui. I'm a PhD candidate in Arizona State University. Today, I'm really happy to present our work, CrawlPhish, analyzing the client-side cloaking in phishing websites. Large-scale phishing is still a threat to the internet users. Attackers design phishing websites, which impersonate legitimate organization ones such as PayPal and Facebook, and distribute those malicious websites to targeted groups of people. Some may be tricked by the fake websites and hand over their credentials to phishers. And phishers can monetize from the legitimate organization using the stolen login info. It causes damages to both users and organizations. The anti-phishing ecosystem has been making joint efforts to mitigate phishing attacks. Blacklist-based anti-phishing systems like Google Safe Browsing and Microsoft Smart Screen use content and URL features to detect phishing. When users visit a phishing website in the blacklist, they will see a warning sign before the malicious web page content. However, according to Google Transparency Report, the number of malware websites decreased significantly, while phishing is on the rise. It indicates that phishing could be more prevalent than malware attacks over time. The increasing number of phishing attacks nowadays is still hurting the whole ecosystem. Some attackers implement cloaking to hide their maliciousness to anti-phishing crawlers and reveal phishing content to real people. In this example, phishers encode HTML in Morse code nowadays to hide malicious URLs. Therefore, browsers that support JavaScript execution can see the phishing content. For browsers that do not execute JavaScript, the content will not show. In another example, phishers know that real people use mouse and move their mouse over the browser, so they detect anti-phishing crawlers using this feature. When an anti-phishing crawler tries to visit the phishing URL, it shows a benign-looking web page because the website knows there is no mouse or no mouse movement over the browser. When a real user visits it and moves the mouse over the browser, the real phishing web page content will show. Previous work has made efforts to mitigate cloaking. This work showed that cloaking techniques, including both server and client-side cloaking technique, can effectively bypass detection by anti-phishing blacklists. Another work analyzed the server-side cloaking techniques and proposed 5 different types of cloaking. However, the nature and prevalence of advanced client-side cloaking techniques implemented in JavaScript is poorly understood. Client-side cloaking technique can be very dangerous because it enables the implementation of complex interactions with potential victims. Therefore, in CrawlPhish, we try to detect phishing with client-side cloaking. To this end, we need to design an automated framework to analyze advanced phishing code. Then we can categorize the cloaking types and measure the impact of the cloaked phishing websites to better protect the ecosystem. Now let's take a look at the framework of CrawlPhish. To analyze sophisticated phishing websites, we leverage APWG eCrime Exchange database, a curated clearinghouse of phishing URLs maintained by various organizations engaged in anti-phishing, and crawl the phishing data with web page source code and a screenshot for each link. To identify whether the phishing websites contain client-side cloaking techniques, which is implemented in JavaScript, we need to focus on the JavaScript included in the website. However, the JavaScript code is very difficult to inspect manually due to its obfuscation and syntax complexity. Therefore, we leverage a JavaScript force execution engine, which can dynamically execute JavaScript snippets of a website and find all possible web page contents. Then the original web page and the force executed page are sent to the analysis engine. We compare the similarity between the original web page and the force executed page in terms of source code and screenshot similarity. Filter out phishing websites with same force execution results. The remaining ones are the phishing websites with advanced client-side cloaking techniques. We also extract such cloaks from the websites in terms of semantic meanings, such as mouse detection or pop-up alert. And finally, analyze the cloaking implementation code to extract web API calls and web events and record them into the client-side cloaking techniques database with the semantic type. Based on CrawlPhish architecture and the APWG dataset, we group the client-side cloaking techniques into three high-level categories. The first is user interaction, which shows phishing content only if visitors interact with a phishing website. This category contains three types, including pop-up, mouse detection, and click-through. For example, in pop-up cloaking technique, the alert window in these websites prevents real phishing content from displaying before click. After the visitor clicks the OK button, real phishing web page content will show. There is an advanced version of pop-up cloaking implementation. Because an alert window can be easily closed through automated browsers such as Selenium, some features instead use the web notification API. But at the time we ran the experiments for CrawlPhish, the automated browsers did not support interactions with notification window, which makes the cloaking technique very hard to bypass. Now one study successfully resolves this problem so that the automated browsers can handle notification window click. Phishers use an instructive web page to lead visitors to click the button on the notification window. As an added benefit to attackers, cloaked phishing websites could also directly send spams to visitors through their browsers. Through this, we show that criminals are using cutting-edge browser features to evade existing detection systems. In the second category, phishing websites with bot behavior identify anti-phishing crawlers based on factors like how long the web page stays open, or whether the web request is repeated after failing initially. This technique includes subtypes such as timing and randomization. In timing cloaking, for example, phishing websites with such cloak deliberately wait for several seconds. Meanwhile, the click here to log in button is unavailable for visitors. After the waiting time, the button is available. And when visitors click through, they will see the phishing content behind. Phishing websites with fingerprinting, which is the third category, identify visitors by inspecting the configurations of browsers or web requests. It contains subtypes such as cookie, referrer, and user agent. We group similar implementations of each cloaking type to track the origin and evolution of each client-side cloaking technique. This CDF of unique implementation groups shows that 20% of the groups account for 74% of all phishing websites. In other words, a small number of reused cloaking code is likely responsible for a significant portion of sophisticated phishing websites in the wild. We also discovered that all cloaking techniques were implemented in phishing in 2018. The CrawlPhish framework was proposed in 2020, which is already the first study analyzing client-side cloaking in phishing. It reminds us that phishers are trying to stay one step ahead of the anti-phishing ecosystem. We suspect that those client-side cloaking techniques may have already been employed well before June 2018, which is the start time of CrawlPhish's crawling process. We also observed the evolution of cloaking techniques from the perspective of obfuscation. From the crawling process, we found that the code obfuscation rate on phishing websites increased from 21% in 2018 to 24% in 2019. For example, for the pop-up cloaking technique, the earliest variant from June 2018 was not obfuscated. Gradually, phishers started to obfuscate their cloaking technique implementations. In October 2018, they added an encoding algorithm to obfuscate the JavaScript snippets. From this finding, cybercriminals are improving client-side cloaking techniques in phishing to make the latest implementation more difficult to analyze. But this obstacle can be conquered through CrawlPhish. It can first execute the obfuscated JavaScript snippets and reveal all possible web page content behind the code. As for the trend of cloaking technique usage, according to the analysis with CrawlPhish and the Crawl dataset, cloaking implementations in phishing grew significantly from 23% in 2018 to 34% in 2019. We believe this is mainly because it increases phishers' profitability or because improving detection systems make advanced evasion necessary. The figure here shows the trend for each cloaking category from 2018 to 19. The usage ratio of fingerprinting category over these 2 years is almost the same. With the bot behavior category, the usage ratio dropped significantly from 40% to 21%. The usage of user interaction cloaking category increases significantly from 2018 to 19. We believe that this is because it is more difficult for unefficient crawlers to impersonate human behaviors that bypass other types of cloaking. We have thus far shown that phishing websites make extensive use of client-side cloaking techniques. We still need to discover whether it is worth for phishers to implement such evasion in the website. By resolving these two problems, first, can these techniques truly evade detection by anti-phishing systems? Second, do they generally let the victims in? We will know the answer. To answer the first question, we deployed 150 artificial phishing websites with user interaction cloaking and reported them to key browser vendors. We found that none of the phishing websites were blacklisted in any browser, except the click-through websites. 21 of them were blocked in Microsoft Edge, with a median of 3 hours after we reported them. The detection occurred because Microsoft Smart Screen classified the obfuscation in the JavaScript source code as malware, not because it could bypass the cloaking technique itself. For the second question, we want to show that those cloaking techniques do not impact negatively for real people. So we generated 3 websites hiding a hello world text behind 3 types of user interaction cloaking, and then hire 1,000 workers to report what they saw after visiting each website. According to the result, mouse detection and click-through technique do not impact negatively showing hidden content to real visitors. But only 43 of the users saw the text behind the notification cloaking technique. The notification window is still useful in phishing, mainly because it's extremely hard to be bypassed, even though fewer people can see the content behind. From all the analysis above, we suggest first, the inefficient crawlers should match the behaviors that the sophisticated phishing kits expect. Furthermore, the ecosystem can implement CrawlPhish framework to the existing crawlers to better detect advanced phishing attacks. We also disclosed our findings to major anti-phishing blacklist operators, Google, Microsoft, and Opera. All companies acknowledged the receipt of the disclosure. Google followed up by requesting more information on the semantics and prevalence of the cloaking techniques, and agreed with the finding that such techniques could potentially bypass detection by current automated anti-phishing systems. In summary, we designed CrawlPhish to detect and evaluate client-side evasions in phishing automatically, and showed that such evasions are very prevalent. With CrawlPhish, we detected and proposed 8 types of evasion across 3 high-level categories. We also found small groups of reused phishing code accounted for a large portion of cloaked phishing websites in the wild. We also disclosed the work to the ecosystem, and hence it improved the ability of the ecosystem to detect phishing with client-side cloaking. Thank you for listening to my presentation, and I will be happy to take any questions. Thank you.